Ladies and gentlemen, a very warm welcome to each and every one of you. I'm Prasadini Vikramasinghe, an engineer by profession and the coordinator for the Greenstan Center of Excellence for Hydrogen. Allow me to briefly introduce the Center of Excellence for Hydrogen. We are dedicated to empowering industry professionals and accelerating the development of thriving green hydrogen economy. Our mission is achieved through industry-leading education, training, and knowledge-sharing initiatives. We offer comprehensive training programs covering the production, storage, transportation, and utilization of green hydrogen, as well as workshops and webinars like this one designed to bridge the knowledge gap. It is also worth mentioning that the Center of Excellence for Hydrogen facilitates collaboration between academic institutions, research bodies, and industry leaders. Our goal is to develop future-proof green hydrogen agenda and equip professionals with the necessary skills and qualifications to succeed in this expanding sector. Before we delve into today's webinar, I'd like to highlight our esteemed partner for this event, PLANCK Technologies. PLANCK Technologies is a dynamic startup focused on developing innovative energy storage materials. Their cutting-edge work is driving advancement in sustainable energy solutions. Now it is my pleasure to introduce our esteemed speaker for today's webinar, Dr. Maryam. Dr. Maryam is a highly respected expert in the field of hydrogen storage technology, and we are honored to have her share her insights with us. Dr. Maryam holds a PhD in chemical engineering from NTNU Norway and has over a decade of experience at Equinor, where she has been at the forefront of pioneering new energy solutions, including carbon dioxide capture, hydrogen, and energy storage. Her expertise is further complemented by advanced management and strategy education from Harvard Business School and Stanford University. Currently, Dr. Maryam leads PLANCK Technologies, where she continues to make significant contributions to the field of energy storage. Today, she will be sharing the latest advancements and potential impacts of their technology. We are fortunate to have Dr. Maryam with us today and encourage everyone to take this opportunity to learn from her extensive knowledge and experience. Please join me in welcoming Dr. Maryam. Over to you, Maryam.
Thank you very much, Prasadini. Maryam Ghadrdan here talking. It's an honor to be here. I'm going to just share my slides. Just a moment. Yes. So today I'm going to talk about the role of advanced materials in the future of energy. Thanks, Prasadini, for the introduction. So no need to talk much here. Chemical engineering by background and energy branch I've been in, and also the new energy topics, which were always exciting. PLANCK Technologies is a Norwegian-based startup. We specialize in offering novel materials for energy storage solutions, be it battery or like longer duration energy storage solutions. And what we have developed so far has been around hydrogen storage. But what are advanced materials? Advanced materials are the materials which are kind of engineered by scientists to perform superior, like to kind of show superior performance, functionality, and properties compared to the traditional materials. And there are many different families of advanced materials. So maybe you've heard about like quantum dots, you may have heard about like nanomaterials, like some smart polymers. and meta-organic frameworks, covalent organic frameworks. So these are different families of materials which could be good for different applications. When it comes to the energy branch, I will just change this so that like you can see the whole slide. When it comes to the energy branch, then there are several applications that we can work with. When I was working in Equinor in the energy in the innovation department, I had one project which was on metal-organic frameworks, one family of advanced materials. And we worked on technology mapping, which is like kind of linking these materials to applications within the energy branch and what they can be used for. And then like you could see that yes, it could be like electrode materials in a battery. It could be adsorbents, like in the context of gas storage, hydrogen storage, or it could be like sensor materials and all the other applications that we could see given one of these materials. And these are all having the common denominator because it's like, for example, since there are some families of materials which are kind of exhibiting highlighted properties like surface area, they can be kind of functionalized. And these are the things that can kind of make them more competitive, kind of compared to the traditional materials. Going to the next slide. It's a bit slow. Yeah, and then I said that like our vertical is energy storage. My last task in Equinor was to lead the technology strategy for energy storage technologies. There are a lot of different technologies within energy storage which can be impacted by materials, advanced materials. And like you can see the red circles around many of them. And then our focus is on like the chemical storage, as I mentioned, and on hydrogen storage because hydrogen is the simplest molecule to be produced. We kind of look at it in the context of energy storage, kind of supporting the grid and supporting the renewable production. And the challenge is that it's not a dense gas. It takes a lot of space. We need to compress it to very high pressures or liquefy it to very low temperatures so that we can kind of store it. So by IEA, International Energy Agency, the hydrogen storage is mentioned as the bottleneck for kind of the hydrogen economy being used in new areas, new markets. Yeah, so this is some information that I have also on the hydrogen, since this is our favorite use case to work on. And 30% of the end user price goes to the storage and transportation of hydrogen. And reducing that, actually, it means a lot, and it can be an enabler to use hydrogen as a long duration energy storage, or like in the other context that they haven't been used before. So our solution is to offer adsorbent materials and adsorption-based storage of hydrogen. In this way, we don't need to go to the extreme conditions. It will be kind of either storing the same amount at at pressure which is 3 times less, or at the same pressure we can kind of spare more and take more of the gas in the same container. But why is it so? This is a short video that I can run here and show. So imagine a fuel tank full of gasoline, and then we want to fill it with gas. It takes maybe some amount of gas, which is just enough to go 2 meters. But then, like you see that the gas is also, the molecules tend to stick to the surfaces. So the point is to introduce new surfaces into the container so that we can store more gas in the same container. And then like some ideas that, what can we do to kind of introduce more surfaces. Imagine sands, then more gas because of sticking to the external surface. What about some sponge-like materials with the internal surface? Then, the molecules can go both inside and outside, and the storage will be much more. And you see that I have a toddler, and we're looking at a lot of Peppa Pig. So going back to my slides. Next one. Yeah. The point is that when we think about adsorbents and using it for gas storage or even in any other application, it's not a simple problem because it's a lot of options that we have. There's one database, CCDC, that we work with, and Cambridge Crystallographic Data Center, and it has more than 1 million material structures in it. So these materials are across multiple families with different properties, different manufacturing complexity, and different cost of the raw material. And that makes it not an easy job to kind of choose which material to use. And actually, many of these materials have not found their way to commercialization because of this confusion in industry of the use cases. What we do in PLANCK Technologies is that we start from the problem side as opposed to the common practice. The common practice is that, like, material scientists, they work on materials, technology and application agnostic. So they offer materials and then they go to industry and kind of try to fit it and solve the problems. But then the thing is that, like, not having this mindset that, we need to also integrate it to the system and think how these materials would work in the system. And then, some materials would kind of meet the wrong application. Yeah, so that's not good for the commercialization of those materials. What we do is that we start from the problem side. We kind of define the KPIs and the system level, and also the safety and sustainability KPIs. We translate them into the molecule level, and we do the material screening in a database of materials. And we kind of select the materials with a top performance, while we also care about the sustainability aspect and the scalability of those materials. And then we do the further analysis by modeling those materials and put it in the system and kind of see what KPIs can they meet. So our aim is to commercialize the right advanced materials for energy storage. Going to the next slide. So I talked about metal organic framework as one family of materials. They are also known as super adsorbents. Just one moment. Yeah. So they are metals or metal clusters and organic linkers, and they can kind of be like a Lego to kind of make any metal from the periodic table, and organic linkers to put them together. That's the point that, they can be functionalized for different applications. They can, for example, be used for hydrogen storage. They can be thought about like for using gas purification, taking the hydrogen out of the flue gas and out of the syngas, and making the process much simpler and cost effective compared to the traditional way. But we also need to be careful about the materials which are toxic, which are scarce, and they have high costs. So these are like the things that we consider in offering the materials for different applications. Looking at how they do compared to the adsorbents in the market from the other families. So we know zeolites and carbon actives and also silicas. So these are kind of the data showing till 2012, which is like 12 years ago. And the development are ongoing. There are some materials which are showing 10,000 square meter per gram. This means that, like, if you kind of unfold 1 gram of this material, hypothetically, you can kind of cover the whole football field with 1 gram. So then, like, what we do is that we define the requirements that what we need from this database, and we kind of focus on the application. Do we want it like for stationary application, for boating application, like where this hydrogen is going to be stored? Is it like a buffer storage linked to renewables? Is it like, for example, storage in a chemical plant to be used for as a feed for chemical production and so on. So we can kind of get what are important factors so that like we come up with a right material and system design for that use case. So this is like how this material screening looking like. So starting with a big database of materials and then like narrowing down by defining different aspects like the thermodynamic stability, stability towards water, which is important in some use cases. And then like we want these materials to be not like with such big voids because it will be a waste of space, but then big enough to kind of take those molecules like the hydrogen molecules into their structure and the binding energy towards that molecule, which is hydrogen in this case, and so on. So we have done calculation. We have come up with like 10 most promising materials. And like these are the things that, you know, we want to do partnership with companies who are working with hydrogen and kind of check what we have developed based on the KPIs that they have, and also further develop and commercialize materials. Here, just a simple example, just to show the swinging between 5 and 50 bars, that like storing hydrogen in these materials, 3.19 kilogram in 50 liters, but for compressed hydrogen, it will be much less, almost 3 times less. So this is like what the whole system looks like. Starting from the materials that like this hydrogen gas goes into the structure, and then we can kind of have some structure in the container. Either we can kind of think about monoliths or shaping these materials as pellets, or have the materials as powder in the bulk system. And then the swing adsorption is a commercial case already being used in many applications. And, you know, the swing could be like either by pressure, by temperature, or magnetic effect, or, you know, some other new technologies are coming up here. This is one case that we have done just to kind of show the potential of these materials for an application. And we did this for, it was like a high-level techno-economic analysis for shipping used on Aframax ship with the specification that they have, like they have a specific dead weight and so on. And then like ran 2 scenarios, one using meta-organic frameworks and then the other one using CNG. And kind of showing here that like with the distance, we see the cost difference between the 2 scenarios, and it will be like in different scenarios, we can see that, you know, one of these technologies could be prevalent. And then we have also like LNG, which is liquefied version, which is now being used for longer distances. And that's also a comparison that would be interesting to do. The levelized cost when we compare is like to the level of $0.1 per kilogram. But, you know, in the context of shipping and the amount of gas which is being transported, then that means around $100 million per year. So yeah, we are a young startup, but we have had a lot of interesting traction so far, collaborating with database owners. We have been talking to clients and are interested to discuss with them about the use cases that they have, and, you know, how we can help and how we can kind of compare and show them the potential of using adsorbent-based hydrogen storage. Member of several networks to kind of have our partners and be in an arena together with different stakeholders from the energy storage vertical. Also, we have been part of several competitions, panel, for example, one panel discussion in the EU Industry Days. We were representing companies in the advanced material industry. And that was a very interesting discussion. Also, just today, we had one meeting. We were invited to discuss and brainstorm AI applications with NVIDIA, who came to Norway to the DNB office. Yeah, and then like we have been also active in the soft funding space. We're in two EU consortiums, waiting for the results, and associate member in one EU consortium which is related to digital twin. Yeah, so several collaborations, as I mentioned, both in the EU projects that we have applied or are in consortiums right now, and also planning to collaborate with Norwegian partners, Norwegian Catapult. They have an arm who is active with advanced materials, and we're working on scalability tests together with them, and with Institute for Energy in Norway. We're working also on like different shaping of the materials and how different shapes are affecting the use case and like the performance of the materials for different use cases. Because like depending on like the use cases, we might have modular systems, we might have smaller or bigger systems, and then shapings could be different for different applications. These are the things that we're active so far. And we have had a very interesting path so far. We're part of Deep Tech Alliance program now, and discussing with the energy companies about the value that we can offer to them. And of course, they are using us to kind of understand more about advanced materials and like the business case studies for the projects that they have within hydrogen. And also, we are planning to do experimentation and collaboration with our partners in Norway, open also for international collaboration. And we are planning to actually have our piloting activities within 2 years. This is the team behind our company. So Hamid and Tim, they are the experts from the chemical engineering side, from the chemistry side, who are complementary skill set that we need for developing the tool that we have developed. And then we have a good group of advisors who are supporting us here. Professor Yang Xiaohun, she's a material expert from MIT. Mohammed Musavi, he's from University of Toronto, and he's the expert in large language modeling and database screening, material science. And we have two very good commercial advisors, Lars Martini and Tim Sonderby, with backgrounds from Haldor Topstoe, Kemor, Adnoc, and they're also supporting us with the business strategy and technology strategy. Aziz is also in the business development team, and we are growing. We're hiring 2 people soon. It's not finalized, that's why their names and faces are not here. But it's a lot of potential, and we see already a lot of interest. And we are also very interested to collaborate with corporates in the problems related to hydrogen, and help them kind of plan for the basic design of their plants and go forward and contribute with a green transition. That's from me. That was the last slide. We'll be happy to take questions.
We are now commencing the Q&A session. Kindly submit your questions in the conversation or raise your hand, and you will be invited to present your question.
It was, as I mentioned, the meeting that we had with them was today. And it was like this discussion was in the context of energy storage and more like in the battery side. But then a lot of comment, in our area, we are on the early phase of the value chain. We're working with materials. And that's why we were invited here to kind of support from the early part of the value chain what ideas can be shared for AI related technology developments within energy storage. So I can update you afterwards when we kind of have more concrete collaboration. But the suggestion that I put on the table was more on the side that, it's the expertise of NVIDIA. They have the toolkit, and they want to kind of help solve the problems which are related to AI. And we have also an AI element. Like what we have developed is a mix of computational chemistry and machine learning. So we use machine learning potentials to kind of reduce the amount of computation and do the material screening. And beside that, another aspect would be to kind of use the ChatGPT type of AI, like the generative AI or the large language modeling type of tool set to kind of evaluate the materials from the sustainability and scale and like the LCA point of view. We have had already one collaboration with Oslo Met where I supervise students on developing a generative AI which can support the LCA life cycle assessment of materials. Then there's another question. The potential machine learning. So I mentioned that. Perfect. Yeah. I will definitely note your email down to continue the discussion. Yes, I see one hand up. Tissa, please go ahead. Still muted. You need to unmute your mic.
Can you hear me now?
Yes. Good.
Yes. Now you are working on towards materials for storage, I like storage for hydrogen. Am I correct?
Yes, that's right. So like in one of the slides, I showed that like these materials are kind of work as a adsorbent. So it's like a sponge that, you can kind of soak the gas in. And then in this sense, then you can kind of make the gas molecules to sit closer to each other. And then like, you need to go to like less extreme conditions to be able to store gas. Because like hydrogen is extreme. I mean the point that the dew point that the hydrogen gets liquid is very, very low, and that's makes very big problems. When I was working in Equinor, and it's the energy company of Norway, we worked on one project with a research center, and they were studying storing hydrogen by compression to 700 bars. But still, at such high pressure, they couldn't show like a good business case because the economics didn't show very good. And 700 bars means that like it's a lot of pressure. It could be very corrosive also. So it should be specific steel and specific thickness to kind of have it safe. So going up to the higher classes of materials for the pipes, it's a lot costlier. And still, again, as I said, the economics didn't show right because Equinor was like considering the use cases related to the renewable energy and how we can store hydrogen in the context of long duration. So that's why I'm thinking that like the new technologies should be evaluated to kind of make better use cases and business cases for the cases where hydrogen is not still there.
Yeah, is it like hydrides, hydrogen? I mean, metal hydrides.
So
Okay.
Very good comment, really, because metal hydrides is also one case which is like solid based storage of hydrogen. But metal hydrides, so it's about a balance that we need, because like metal hydrides also have high capacity. They do, I think, more like a chemical absorption. So it's more like energy intensive. And then other point is like that, because like in metal organic framework is metals and organic linkers. And of course, I mentioned that, we are also using covalent organic frameworks, which doesn't have metal. So then the weight kind of becomes a factor, because metal hydrides have been studied for the boating industry, and it then show as a good case because of the weight. The other point is that metal hydrides, like since we need to kind of regenerate the hydrogen, take the hydrogen out of the structure, this has been somehow a problem, because like the cyclability of metal hydrides were not that good. So depending on the use case, that like, how many cycles one have, and the numbers on the use case makes one technology more valid than the other one.
Okay. Thank you.
You're very welcome.
Hi Maryam, Ritika here. I just had a question, like, what methods are employed to dissolve the gas from the inert materials in the database? Because given that these materials are initially unreactive with the gas that they absorb, what is like generally used? What kind of processes are used to dissolve the gas that was initially absorbed?
Yeah, good question. So it's like also the common swing absorption method that can be used. We
Right.
have worked up pressure swing absorption. So like it means that, if you have the higher pressures, then you can kind of force the hydrogen to go into the structure of the materials, and when you release the pressure, then they can come out. And then you can do the same with the temperature. So a swing of
Right.
temperature is also one way that people do to kind of do the absorption and desorption. So what happens with these materials is like a physical absorption, and that kind of gets triggered by either pressure or temperature or even magnetic fields. So like for the magnetic field, it's even a special case. It's like a new technology which is coming up, and one may need to kind of think about the materials which are reacting to that magnetic field. So it will be a specific case, and like um, one set of materials which are called magnetocaloric.
Right. Thank you.
You're very welcome. I'm reading the message from Dr. Tushara. So he's working also on developing ML algorithms to select catalytic materials for hydrogen generation, using solar powered water splitting. That's quite advanced and interesting technology. Yeah, that's nice.
Pritika, you can deliver the word of thanks.
Sure. Thanks, Prasadini. So, as we conclude this insightful webinar on green hydrogen storage solutions, I would like to extend our heartfelt thank you to all of you for your participation. And first, our deepest gratitude to Dr. Mariam. Your expertise in chemical engineering and your extensive experience at Equinor, along with your prolific education, have provided us with valuable insights. And your discussion on the innovative AI equipped computational chemistry, machine learning equipped um, energy storage database that is developed by your PLANCK Technologies has been both inspiring and informative. Thank you for sharing your knowledge and vision with us today. I also want to
My
take a
pleasure.
moment. Thank you. I also want to take a moment for honorable mentions, starting from USAID and SAREP for their invaluable support of our programs in Sri Lanka and India. To our wonderful audience, thank you for your time and active participation. Your engagement and thoughtful questions have enriched our session and highlighted the collective interest in advancing sustainable energy solutions. Together, we are taking significant strides towards a more sustainable and energy efficient future. So, once again, thank you, Dr. Mariam, and wish you success in all your future endeavors. And thank you to everyone who attended. We look forward to seeing you at our future events. Thank you.
Thank you, everyone.